I'm going to say something controversial. I think we need to stop teaching free body diagrams. I don't mean we shouldn't teach forces, and I don't mean we shouldn't teach forces as vectors that exist in 2, nay, even 3 dimensions. And I'm not saying we shouldn't teach that the sum of all forces on an object equals dp dt. And I'm not saying we shouldn't draw diagrams to help us determine the sum of all the forces. What I mean is I think we need to step back from teaching free body diagrams as an ideology in Physics 1. Because there's this trend in a lot of Physics 1 classes, including Physics 1 classes that I'm involved in right now, that the whole goal is centered around free body diagrams. And the reason I say this, the reason I say we need to take a step back from this as an ideology is because why are we doing that? We're not doing it for the physics majors in the room. Because after the Physics 1 class, they're never going to touch a free body diagram again until they go to teach Physics 1. I don't sit around in my office doing free body diagrams for my research. I don't know of anybody in physics who sits around all day for their actual physics work drawing free body diagrams. We do it to teach in Physics 1. And then when we go to teach upper level classical mechanics, they're not there. Because we're more interested in getting to the Lagrangian, the Hamiltonian, normal modes of oscillation, non-constant forces, for crying out loud. So why do we teach it? Why is it even in the course? Well, it's there because our engineering students need it, right? It's there because the majority of the folks in that Calc-Based Physics 1 are headed off to engineering, where we tell them they're going to need free body diagrams. Let's analyze that logic for a second. First of all, it's centering our entire course around one student population. And yeah, even if they're the majority in the room, they're not the only students in the room. Chemistry majors, to my knowledge, don't need free body diagrams. Math majors certainly don't need free body diagrams. And the biology majors over in the algebra-based physics course, an entirely other course, okay, yeah, maybe they need a little bit of it for if they're going into kinesiology or some applications of anatomy and physiology, but they need, well, we'll talk about what they need. I'm getting ahead of myself there. But let's be honest, the main reason we have it in algebra-based physics is because we're already teaching it in calc-based physics, and we want those classes to be as similar as possible to minimize our prep time. That's another topic for another time. But why are we centering this entire course around one group of students? And in fact, it's not even that entire group of students, because that's just the mechanical engineering majors. What about the electrical engineering majors? Do they do free body diagrams? I don't think so. They do circuit diagrams. So yeah, let's load up Physics 2 with circuit diagrams. But why the force diagrams for the electrical engineering majors? Why the force diagrams for the civil engineering majors? Maybe for the structural engineering majors a little bit, but don't they need some material science as well? But my point is, why in this 15-week course that's for this wide range of students, are we so set on this one topic, this one skill set, that really only serves one major, maybe 1.5 majors that are in that population? Because what ends up happening is we end up spending so much time on free body diagrams and making sure they get the components decomposed correctly and making sure they get sum of all forces in the x direction and sum of all forces in the y direction, and the one time they need it, the sum of all forces in the z direction. Why are we spending so much time on that we push energy to the side? Because the mechanical engineering majors, they need energy too. The electrical engineering majors definitely need energy. The chemistry majors and the biology majors, oh boy, the main thing they need is energy. And let's be honest, the thing our physics majors need is energy, because that's what quantum is based on. This is what classical is based on. And let's be honest, an energy curriculum is what our society needs. Free body diagrams are not going to solve the climate crisis. But a better understanding of energy and thermodynamics and entropy and what happens when you start just letting energy loose into the environment, that's going to help raise up a generation that can help solve the climate crisis. So what does this have to do with computation? Why am I talking about this on Computation Thursdays? Well, because free body diagrams are also kind of a not great problem for computation. I've done it. You can do free body diagrams in GlowScript. They look nice. It's not really a computation problem though, right? Because you have to go and solve the problem by hand and then make a visualization of it. You might as well just draw the thing, or open up MS Paint and draw it. As you're kind of just adding layers of complexity to it there. There's not a whole lot of computation to do with free body diagrams. There is a lot of computation to do with forces. We love our Euler-Kromer algorithm. But Euler-Kromer does best with non-constant forces. And when you're stuck on free body diagrams, and you're stuck on the tension in this cable and the tension in this cable and the friction on the ramp, you're talking about constant forces. You're not going to get the full effect of computation. You're not going to get the full power of using these devices in your class if you only do constant forces. Because by the time you start doing drag and springs and gravitational forces, yeah, you can draw a free body diagram on it, but the free body diagram is not the point. You're not doing a sigma fx equals max and sigma fy equals may. You're getting into Newton's second law now as a differential equation, the thing it was meant to be, right? Newton invented calculus to be able to solve that equation. And every week we spend just plugging more constant forces in, we're underutilizing that equation, and we're underutilizing our computational resources. And then you can take those computational resources, you can start looking at the energy. You can start looking at what happens to the kinetic energy and the potential energy. You can start looking at what happens to the total energy of the system when you have dissipative non-constant forces. So that's my encouragement to folks this week, is to just think about, really sit down and assess how much time are you spending in a semester on free body diagrams? And how much time in a semester are you specifically spending on constant forces? That's my thoughts for this Computational Thursday. Would love to hear your feedback in the comments or on Twitter. Thanks so much for watching. I'll see you next time. Bye-bye.